So, good morning, ladies and gentlemen. My name is Roland Kircher, and I'm glad to have this first session in the morning about transportation systems. And the first speaker, the first presentation is from Reinhard Rampelmann from Thyssen Group company, and he was a project manager of Transrapid in Shanghai during the implementation and service, and now he's also doing the contract managing, and he will report about service experiences, maglev vehicles in Shanghai. So, please.
So, good morning, ladies and gentlemen. I want to give you some information and experience out of our operation experiences of the Shanghai maglev line. I divide this presentation in three parts: short overview about the project, then the system concept of the vehicles which are relevant for the maintenance strategy, and finally about the maintenance of the vehicle. So I think everybody in this room knows the Shanghai demonstration line from the Pudong airport to Longyang Road station. Unfortunately, not really into the center of the city, but for the demonstration, that's fine. We have a line with a double track, 30 kilometers long, 3 vehicles, and this line is fit for circular operation with 3 vehicles out of 5 cars, and as well as for a shuttle on 2 tracks. Here are the main features of the line. We have a maintenance center aside with 3 tracks, and as Professor Lin yesterday stated, the track is fit for 430 kilometers per hour. So the short overview about the amazing time schedule of this project. In May 2000, Premier Minister Zhu Rongxi visited Emsland facility, and half a year later we have the contract in the pocket, and overall after 3 years we can go into the operation in April 2004. I think these slides are well known from yesterday. That are the operation statistics and the availability. Professor Lin Gubin has some updated data. This one is from the last maglev conference. So now let's come to the relevant vehicle concept, which is the key point for the maintenance strategy. So we have in our vehicle redundancy functions which allows to continue operation for a tolerable predefined time in case of failures. The repair of single failures of the redundant system at an early time avoids multiple failure combinations, and due to autonomous supervision of components, switch off of the failed components, we are able to continue the operation until the daily operation has finished. And just in a multiple failure case of several components, we have to take out this vehicle of operation and substitute it by another, but that's a very rare case. The second key issue for the maintenance is perfect diagnostic systems, which gives us at time of a single failure, the exact information, what happens, what are the consequences, and we are able to prepare countermeasures for the daily maintenance in the night shift. And third key feature of the vehicles are easily exchangeable units of the electronic components by slide-in units and independent subsystems which makes the maintenance easier and or easy, and the experience learned that the concept was 100% as we expected. So here you see an example of a slide-in unit of an electronic component, for example, magnet control unit can be handled by 2 persons within shortest time. Take out the defective or and slide in the new one, which is tested beforehand, and that's all. Second example is a complete magnet module. We have prepared it in the warehouse in case of some expected failures. You just exchange the complete magnet module, including the sensors, magnets, and so on and so forth. So let's come to the maintenance itself. We have, I want to address the spare part strategy, the maintenance concept with the maintenance management system, and a short overview about the experience. First of all, don't be afraid of the text that's just also written in my report. We have scheduled and unscheduled maintenance measures. The scheduled maintenance measures are the daily measures from the visual inspection of the incoming vehicles until to some singular tests. And of course, in case of some failure indications, exchange of these defective components. And before start of operation, again, we have a function test of the safety relevant functions like brake, for example. And the second is long-term maintenance measures, which needs longer time and which can be planned in normal. So regarding the spare parts, we have a complete amount of spare parts. That's round about the amount of electronic components and key mechanical elements regarding one levitation guidance system of one section. Roughly, the spare parts inventory is calculated on the expected lifetimes, the number of components which are in one vehicle or in the complete fleet, the reliability of the fault tree analysis, the recovery time, and last but not least, the time lead time which is needed to resupply such spare parts. We have in the maintenance area a set of tools which are needed for the mechanical part, as well as testing devices for the electronic boards. Then we have a maintenance management system which has on the one hand operational data of the vehicles. In this maintenance management system is the maintenance program of the vehicle. I will come to this a little bit later, and maintenance instructions. I mentioned already the data diagnostic systems and the recording of the maintenance measures itself. So let's jump to this maintenance program and the instructions. We have a based electronic version of the maintenance manual where you have the all the program issues. You have the manuals, operation manuals, the records of the maintenance, and it is divided in you can select by components here or by functions, and you will see here in the example for the related documentation. So regarding the spare part supply, we are happy due to the low stress level of the components. Most of the components are still alive from the first day of operation, and in case of repair, in the meantime, you know, the electronic components, we have a market which is changing relatively quickly, but we, on the other hand, are observing this market situation and can take care of timely substitutes and concepts. So, all in all, I can tell we are, from our point of view, in close touch with the operator, and from our experience, everything happens in that way, and maybe even better than we expected during the contract negotiations. So, thank you very much.
Thank you, Mr. Rampelmann, for your interesting presentation. We have time for just one or two questions. Yeah, please. Question? No?
Yeah, he has a question.
No. If there's no question, then thank you again, Mr. Rampelmann.
So, welcome.
Now we proceed to the second presentation, and we have a slight change in the program. Instead of the presentation of Mr. Ye Li about the characteristic research of collector-contact relation, we have a presentation by John van Rosendale about permanent magnet-based maglev using low-frequency null flux stabilization. Mr. Rosendale is retired director of the College of William and Mary from the United States. So please.
So director of computational science, not of the college. I want that to be clear. So I'm John van Rosendale, and I'm retired, as it says there. I'm John van Rosendale and retired from William and Mary, working on maglev. And I'm going to talk about Okay. Okay, didn't work. So here's a quick overview of the talk. I'm working on a system called MagFlight. It's a permanent magnet-based high-speed maglev. And permanent magnet levitation systems are attractive because it's so simple, but it requires an electrodynamic stabilization system. Here's a picture of the system overview. It looks more or less like that. This is on a raised guideway. So my system is similar to InductTrack. InductTrack was designed by the late Richard Post at Lawrence Livermore National Lab. InductTrack uses Hullback arrays of permanent magnets on the vehicle, and then it stabilized by a high-frequency Hullback array system, and there's various forms of it. InductTrack 3 was designed for low-frequency the low speed and heavy loads. And one version was tested in the Port of Los Angeles for moving cargo. So my system is similar. This is a patent drawing of Induct Track 3. That's the patent drawing. And I'm doing something quite similar. The difference is that I'm not using the 1D hullback array. So here's a quick overview of my system, and here's a more detailed view. So there's a large neodymium magnet, and then there's pole pieces. In the top of the guideway rail, there's steel laminates, and then here's the stabilization system. So that's a quick overview, and it's a guideway that has two vertical rails as shown. So all the magnetic interactions occur on the vertical surfaces. So here's a picture of a finite element computation of the fluxes. So the magnet is at the top, and then there's large pole pieces. The field in the gap there is about 2.4 Tesla. And here's the iron plates, the laminated plates in the top of the guideway. Here's a picture of the forces you get. The black line is the force. So if you displace it, it's shown in centimeters. Gradually the force rises and then reaches a peak, and then it drops off. The red line is the stiffness, or the derivative of the force. And you can see that at the peak there, the stiffness goes to 0 and the system goes unstable. So that's shown here. So you want to be in this blue region where it's stable, and we're seeing order of 45 kilonewtons in a magnet that's 1.5 meters long. And this is unstable. You want to stay away from this. So in the stable region here, the stiffness is about 8 kilonewtons per centimeter. So now talking about stability, here's a picture of the magnet attracting the laminated iron in the top of the guideway. And if you look at stiffnesses, there's the Z oops, I want to go back. So there's vertical stiffness, horizontal stiffness, and longitudinal along the track. And if you look at the proof of Earnshaw's theorem for the normal case where second derivatives don't vanish, it's trivial to show that the sum of the three stiffnesses have to be 0. And since the stiffness in the guideway direction is 0, that implies that the more stiff it is in the vertical direction, the more unstable it is horizontally. They come together. Good things come with bad things. And as I said before, we're at about 8 kilonewtons per centimeter in instability or stability in the vertical direction. So what to do about this? So this is a fairly springy system, soft system, and I can make it stiffer by adding more poles. If I do that, I also have to increase the stiffness of the stability system. So you get a trade-off there. There's an engineering trade-off. You either have more expensive magnets on the vehicle in a soft system, or less expensive magnets, but then you have to put more induction coils in your guideway. So now talking about frequencies. So in duct track, there's a Hallback array as shown, and it creates AC voltages in inductors in the guideway. If you look at that, then there's the equations for the field of the Hallback array, and you find that the frequency, well, first of all, to optimize stiffness, you need, if the spacing here is maybe a centimeter away from the inductors, then you find that the optimal pole spacing is about 6 centimeters, 2 pi times that. And if you look at that for a high-speed system, you get up to fairly high speeds, high frequencies. You get in 400 kilometers per hour, you'd be at almost 900 hertz. If you get to 600 kilometers per hour, you're at 1300 hertz. So what I noticed is that you don't have to do it that way. You can use a 2D array where you have one spacing PZ here for vertical spacing of poles and a different spacing PX for horizontal spacing. And so you can choose PZ to optimize your system stiffness and PX to optimize the frequency. If you do that, you can get to any frequency you like. And here's a different geometry that does the same thing. In this case, I have slanted poles and slanted inductors like that. So by choosing the ratio, we can choose any operating frequency we like. So for example, we can run at 20 to 200 hertz, and that corresponds to a range of speeds from, say, 40 to 400 kilometers per hour. And that gives us a system that we can choose the operating frequency we like below that minimum speed. Because this is an electrodynamic system, we need rollers like on a roller coaster to stabilize the system. So the system is very efficient. There's almost no losses. There's hysteresis in the iron laminates in the top of the guideway. And there's also some tiny eddy currents in general, but on curves, when you use the null-flex system, you get significant eddy current losses. So it's by choosing a very low frequency, we can also use aluminum inductors in the guideway rather than copper. Aluminum is about per amp of current, it's half as expensive as copper. Some of the InductTrack systems actually use copper Litz wire for the high frequency, which is double the price of copper. And just a little bit about propulsion. Here's a simple system where you have a propulsion system in the middle. A better system, you use, it's hard to see, but there's gaps in the iron plates here, and that works with a reluctant synchronous motor. And so you get the same iron plates work for both the stator of the motor and for levitation. And so there's the full system. So it's a new system, similar to InductTrack 3. It's very efficient. Permanent magnet-based levitation is convenient, foolproof, and so on. And it could also be used for the Hyperloop. InductTrack is being explored for Hyperloop, so this could work as well for Hyperloop. And so that's this talk.
Thank you, Mr. van Roosendael, for this nice presentation. The presentation is open for questions. No? If there are no questions, then we have another change in the program, and it will be not the last one. The next presentation of Mr. Chung Hui Dai is replaced by another presentation by Mr. van Roosendael about bimodal maglev interoperable with conventional rail infrastructure. So I think the presentation is included. Okay. The second presentation. Right. Okay, then I would like to ask you to continue with the second presentation.
So I'm the same person I was a minute ago, so I won't do it again. So railroads connect the cities of the world. Here's a picture of Europe, of course, and you can see just many of the railroads there. There's 1.3 million kilometers of railroad right-of-way worldwide, and so the track is many times that. Oops. It doesn't move. So here's just some of the infrastructure. You're all aware of this. There's bridges, there's stations, track work, and replacing this, I mean, that's the fundamental issue with maglev, is replacing all of this infrastructure is very, very hard. It's particularly hard in urban areas, such as cities where you can't easily get new right-of-way. There's a tunnel in New York City being replaced, and just to put in new vents for the tunnel, they have to tear down apartment buildings worth many millions of dollars. So fixing city infrastructure is very, very hard. So my idea was to use a high-speed maglev that can operate on both conventional rail and maglev. And so the advantages, you can use existing infrastructure, and you can use maglev in the countryside where you can go fast and get all the cost and maintenance benefits of maglev. The disadvantage is that the trains are more expensive because they have two kinds of components, and the engineering is fairly difficult. And I should reference Dr. Jesse Powell, who had similar ideas some years ago. He patented it, and the ideas here are patented as well. So here is the maglev system I just talked about. It's called MagFlight. And here is a conventional powered truck or powered bogie in Europe, truck in America. I have a geared motor and train rails. It's riding on the track. And when I put them together, I get a system like this. So it has maglev components at each end, and then it has conventional components in the middle. When I'm on track like that, the maglev components do nothing. They just hang there and don't do anything. When I'm on the guideway, the maglev components support everything, and the conventional part in the middle functions as what they call a span bolster. So there's something called a Schnabel car that has multiple trucks or multiple bogies supported on a span bolster, and that's all I'm doing here. So the system is designed to work with conventional infrastructure unmodified. So the same stations, the same grade crossings, everything the same. And for that, I need to live with passenger loading gauge. So here's a standard North American gauge. And there is no change at all to the passenger loading gauge. So it works with unmodified infrastructure. To change, I go through a special transition region here, shown in turquoise or blue. And the transition operation, you simply go into that special region and you pick, the maglev picks the train off the rails. It takes about 5 centimeters of movement to transfer weight completely from rail to maglev or vice versa. And here's just a sideways schematic of that. So here we're on railroad track, and all of the weight will be on the track. And then as you transfer, there's a slight grade here. It's less than 1% grade. And halfway through, you're equally supported both ways. And by the time you get here, you're entirely supported by the maglev system. And here's a video I made of this.
Railroads interconnect.
Is there sound?
High-speed rail is fast, convenient, and environmentally friendly. Maglev would be even better, except that it's incompatible with the vast existing rail infrastructure. Maybe this doesn't have to be. MagFlight is a new form of transportation, blending conventional and maglev technologies. MagFlight trains are fully compatible with conventional rail infrastructure. But then, running through a special transition section, MagFlight trains shift from conventional rail to maglev guideway. Magic! Here, in flashback, is an X-ray view of both the conventional and maglev components. As the train advances through the transition section, the maglev system lifts the wheels off the rails. Voila! A maglev train. MagFlight uses a new, highly efficient, permanent magnet-based levitation system. Aerodynamic drag will be the only significant energy expenditure, making this system quite environmentally friendly. To convert back to rail, the train simply runs through the transition section in the opposite direction. Did we mention that MagFlight is environmentally friendly?
So here's the cross-section of the MagFlight system. You saw that in the last talk. And the only complicated technical issue here is guidance as you transfer from the maglev system to rail and back again. I think everyone here knows that rail systems, you don't usually use the flanges to guide the rails. What it does is a system called coning, where if the wheel set is off center, then this contact point will have larger circumference than this one, and that twists the truck and makes it center again. And so that's the system we have for guidance on rail. On the maglev side, we have the stabilization system, which is normally weaker, and so there's a compatibility problem there. And so the system I patented has a compliant support for the rails in that transition region. So for the first half of the transition region, you have a compliant system, and it can use either just air cushions here and I-beam connectors, or you can make a hydraulic system like this. So just conclusions: MagFlight's new permanent magnet-based maglev system that uses low-frequency, no-flex horizontal stabilization. And this talk showed a version of that that's intercompatible with conventional rail. And the system is designed to use existing rail infrastructure, making it easier to deploy maglev.
Thank you very much, Mr. van Roosendale. We have time for a couple of questions. No question? I have one question. So, this is a very interesting approach to combine the maglev system with a conventional railway system. What is the big advantage of combining these two systems or integrating these two technologies into one system?
So the advantages of combining in the cities, you get to use conventional infrastructure, all the stations, the grade crossings, the track, all of that stuff that every country has. But then you get the low maintenance and high speed and smooth running of maglev in the countryside. So you still need to do new infrastructure, but it happens out in the countryside where it's much cheaper to do.
Okay. No, thank you. So we have some more changes in the program, and I want to first confirm that Professor Zhao is he attending this session? Okay. Then Mr. Zhao from Chengdu University, he will give a presentation about curving performance of medium low-speed maglev vehicle considering nonlinear characteristics of air spring suspension. So please, Professor Zhao, the floor is yours.
Hi everyone, good morning. Thank you. Pay attention to our research on the curving performance of the medium-low maglev vehicle consider non-lined air spring separation. First, I'd like to introduce the research's background. As we know, the air springs are used widely in modern rail vehicle as the secondary suspension and some of the automobile. The left picture shows the rolling low-bow air spring. This kind of air spring usually used for the railway vehicle, and the left is the convoluted air spring. It usually used for the automobile, and the middle picture shows the sleeve type air spring, or the EMS maglev vehicle usually the type of air spring. Now let's look at this type of air spring structure and the operation springs. So this picture shows the air spring, including some components. This is the calipers and the air bellow and the lever valve. So the lever valve is measure the carbon vertical displace and determine the air input and out to the air bellow. And some airplanes use the different pressure valve. It is the balanced pressure value of between the left and right the air spring pressure. So it can be concluded that the air spring suspension is a complex non-linear system, and it can affect the dynamic performance of the maglev vehicle, such as to the stability of the electromechanical navigation and the climatic envelope of the vehicle and the cabin performance data. And the additional, the air spring of the maglev vehicle is different from the railway vehicle. Usually the railway vehicle just have the 2 air springs, but for the maglev vehicle, for the 5 unit of the from the non-speed maglev vehicle, there is the 20 air spring. So how to configure the air spring of the maglev vehicle, and how the air spring is influence the dynamic performance of vehicle. We have a little research on it. Secondly, I would like to introduce the dynamic motor of maglev vehicle concerned with the non-linear air spring. First is to give the navigation control motor. This shows that the completely controlled fiber. This is the field and the control and sensor. So we used the SimPark software, used the mass similar interface and building is the navigation controlled motor. This shows the basic controlled law and the electromagnetic force. Then this picture shows the non-linear air spring motor. We use the SimPark, the air spring interface, building the air spring motor. This shows the force formula and the pressure formula and the volume formula. This figure shows the vehicle dynamic motor. It shows that the low-speed maglev, including the 5 suspension forms and 20 DOF have been canned. This shows the top value of the 3-car trains dynamic motor. Suddenly, we introduced the numeral simulation results about the carried behavior. So we considered 5 different air spring control must. The first here is that there are 12-point suspension. 1, 2, 3, 4, 5, 6, the legs and the right. So the total 12-point suspension. Now we consider the 6-point suspension, 5-point suspension, and 3-point. And the temperature conditions, including the vehicle speed is 100 per horse, and the cabin length is 200 meters, and the cabin radius is 500 meters. This picture shows the calculated results about the co-bodied vertical displacement. Can you find that the linear air spring just don't consider the non-near wells. We find the co-body can return to the initial vertical place. But for the non-geared motors, the cargo vertical place is different from the initial valve due to the input and output, the L. And we can find the 6-point controlled mass may lead to the minimal carbon vertical displays after the vehicle passed through the car. This shows the different controlled mass, the navigation gap and the electromotive force. So Mr. Cam shows that the different air spring controlled mass affect the magnetic gateway interaction. So finally, I will give the conclusions. Based on our research, it can find is very necessary to consider the controlled non-linear air spring and the levitation control system in the magnetic numeral analysis, because the non-linear characteristics of air springs affect the dynamic performance. And the second, when the air spring system uses the 6-point suspension, where the cavity performance of the vehicle is better than the other suspension last. So I think this research can be used the secondary suspension design and the optimals in the next work. That's what. Thank you.
Thank you very much, Professor Zhao, for your interesting presentation. We have time for a couple of questions. So, from the auditorium, no questions, and we are very good in time. And thank you again, Professor Zhao.
Thank you.
And I have to confirm, Mr. Yang Feng, is he? Okay. Okay. Then we have some more presentations in this session. I've informed about several changes, but we are right on time, so no problem. So, Mr. Yang Feng, you are from Chengdu University in China.
Yeah.
And his presentation is about dynamic mechanical behaviors of secondary air spring suspension of high-speed maglev vehicles running over the curved track. So please, Mr. Feng.
Yes, thank you, Chairman. Hello, everyone. My name is Feng Yang from Southwest Jiaotong University. And my topic is the dynamic mechanical behavior of secondary air spring suspension of a high-speed maglev vehicle running over the curved track. At first, I will introduce the background of the research. Then the high-speed maglev train dynamic model will be given and described, especially the nonlinear air spring model. After that, I will show some results of the dynamic mechanical behavior of secondary air spring. Finally is the conclusions. And as we all know, from 2000, the first high-temperature superconducting maglev test vehicle was born in Southwest Jiaotong University. Step by step to the 2016, the CRRC declared that they want to start the 600 km/h high-speed maglev project. And based on the Transrapid 09 in German and the Shanghai high-speed maglev commercial line, in order to develop the new generation high-speed maglev train, which the max speed can reach to the 600 kilometer per hour. We plan to simplify the secondary suspension system to use the air spring. So the secondary air spring plays a crucial role in the maglev operation. And we always use the linear spring damper method to simulate the air spring. But in fact, the air spring is just like this. It is a nonlinear and very complex system through the air input, air output to change the inner pressure and to change the vertical force of the air spring. I use the FMU interface in SIMPAC to realize the co-simulation between the AMSIM and the SIMPAC. AMSIM is a professional pneumatics software to simulate the air spring. So that means I can establish the air spring model in the AMSIM, considering the level control valve, considering the gas bag or the other details components of the air spring. Then establish the vehicle dynamic model in the SIMPAC. By the way, I use the MATSIM interface to simulate the magnet guideway interface relationship. So this is the high-speed maglev train dynamic model. And there are 3 vehicles in total and 4 levitation frame per vehicle. And there are 4 nonlinear air springs on every levitation frame. So there are in total 16 air springs per vehicle. And it's a problem to how to control the 16 air springs. We can see here. Okay. If the air spring with the same ID means the air spring controlled by the same level control valve. The air spring control strategy just like the 4-point suspension in high-speed railway. And this is the details of the levitation frame dynamic model. And here are some results from the simulation. At first, in this graph, we simulate the high-speed maglev train running over the horizon curve at a constant speed. And the red line is the result from the the result of a vertical air spring force using the nonlinear air spring. And the black line is the linear equivalent air spring model. We can see that no matter which air spring model used, it is the same trend when the high-speed maglev train run over the curve. But we should make the point that that's the difference between the red line and the black line. The vertical force vibration value is small when use the nonlinear air spring. Is smaller than the black line, and about 42%. And we can also see the under the function of the level control valve, the vertical force is stable slowly in nonlinear air spring. Here and here. That's because of the air spring input and output, the air input and output processing reason. So it is very clear that it is very necessary to considering the nonlinear characteristics of the air spring in high-speed maglev simulation. And then we use this model to simulate the maglev train run over the horizon curve with different radius from 5,500 meter to 8,000 meter at the speed highest speed about 600 kilometer per hour. We can see that the carbodylateral displacement can reach to 90 millimeter, with the radius is 5,500 meter. But it just here, it just 40 millimeter with a radius of 8,000 meter. The result can provide a limit value of the guideway design and the air spring or the second suspension design, because there are not there are the limited lateral space under the car body to arrange the air spring. And we also use this model to simulate the maglev train run over the vertical convex curve with different small radius from about 1,000 meter to 530 meters, and at the lower speed. We can see when the high-speed maglev running over the radius is 530 meter vertical convex curve, the load of the fourth and the fifth air spring increased to 85 kilonewton, and the load of the first and the last air spring decreased to 20 kilonewton, and the displacement of the fourth and the fifth air spring increased to 48 millimeter, and the displacement of the first and the last air spring decreased to the 70 millimeters. And here are some statics data from the vertical convex curve. We can see that the dynamic response of the air spring increased with the decrease of the vertical curve radius. And when the radius is 530 meters, the force air spring force variations value reached to the 50 and 5 kilonewton. And the first air spring vertical displacement, you can see here, can reach to the 70 millimeters. Not only this, but also we can use this model to simulate the details parameters of the level control valves, just like this. The level control valves is the most important component of the air spring, such as the deadband and the delay times and the rate of flow. We can also use this model to realize it and find it. And finally is the conclusion. We know it is very necessary to considering the nonlinear air spring because it is very significant difference between the nonlinear air spring model and the linear air spring model. And then the result from the high-speed maglev train dynamics model with considering the nonlinear air spring can provide many advanced limit value for the secondary suspension system design of new generation high-speed maglev. And the last, the model can also be used to analyze the detailed parameter of the air spring. Thank you very much.
Thank you, Mr. Feng, for your nice presentation. We have time for questions. No? If not, then thank you very much again. Then I've been informed about an additional presentation by Mr. Akira Heya from Osaka University. May I ask who will give the presentation? No? Okay. If this, then we continue to the next presentation, and I'm glad to introduce Professor Gino Dovidio from the University of L'Aquila in Italy, and he will give a presentation about innovations and performance of Italian UAQ4 superconducting magnetic levitated systems. So, please.
Thank you, Mr. Chairman, for the introduction. Good morning, ladies and gentlemen. As reported in the title, in my presentation, I introduced you the Italian UAQ4 superconducting magnetic levitated system technology. The presentation overview foresees the UAQ4 train project, history, feasibility, and performance of technology. We introduce the propulsion energy calculation, we speak about magnetic resistance, and finally remarks and outlook. The UAQ4 is the acronym of University of L'Aquila Model 4. It is an under development project of superconducting levitating train. This project is the results of over 40 years of Italian research activity in the field of non-conventional transportation system. He started in 1917 with the construction of IAP2 prototype. We have the movie, but now it doesn't work. And it was used. No, please come back. Okay, used who shaped guideway and air cushion for suspension and propeller for propulsion. In 1973 was constructed the IAP3, the second prototype that introduced the first one-sided linear motor and the active suspension on board. And in 1998 started the UAQ4, the innovation of which I will show you. This project was started to study, define and test technological solution with the aim to eliminating any magnetic drag to motion. This is a key point because the current systems do not achieve the full potential advantages of magnetic levitation, since suspension is still affected by magnetic resistance. Realizing a levitation system to lift and guide the vehicle with a lowest electric power consumption, and realizing a system architecture with standard close to aeronautical one. The suspension and propulsion device feasibility was fully tested in the laboratory. The results are shown in the movie. The bogie motion is magnetic drag-free. It is self-stabilizing and it floats smoothly above the track at standstill and in all phases of motion at large air gap, and no power consumption is required for levitation except the negligible amount needed for cooling the superconductors. This is the levitation working principle is based on the interaction between superconductors and magnetic field of permanent magnets in a V-shaped geometry. Propulsion and braking are performed by a novel DC linear motor. The system architecture is based on aeronautic standard, materials, size, and comfort, and we designed the cabin in a very similar kind to an airplane fuselage. This activity is ongoing, and we are designing our system by a tridimensional virtual immersive reality model. Now introduce you the propulsion energy, calculation resistance, and magnetic resistance. It is well known that the propulsion energy depends on power, electric power energy necessary to power the vehicle. The electric power energy is function of motion resistance. We can divide this resistance in two main groups. The first one, there are aerodynamics, gradient, and inertial. In the second one, we have additional magnetics force resistance that depends on the kind of technology. To calculate the magnetic resistance, we start from a study published from two authors, Stefan and Lossier. I don't know if they are here. That proposed a method to calculate EMS and EDS resistance. I jumped the method, but this resistance depends on different parameters for each systems. They compared this resistance for a standard and fixed configuration trim. For what concerning our technology, we tested the magnetic resistance to motion by an experimental device that allows to measure the lift and magnetic resistance by varying the air gap and the relative speed between the superconductors and a track. The results are shown in the figures. We can see that we have not magnetic resistance by varying relative speed between superconductors on board and magnetic track. What it means? That this system allows to reach lower consumption energy consumption. We have fixed a standard train, and we have compared the results. Combining the results of Stefan and calculation with our test results, we can show the comparison. The first red one is EMS, ADS, and blue one is EMS, and the third is our technology. We have also, I'm concluding, we also compared the magnetic resistance with the rolling resistance. For this, we considered a wheel-on-rail high-speed train, Italian ATR500, and compared the results. We can see that in terms of resistance to motion, the wheel-on-rail system is more efficient at low-medium speed. Vice versa is lower efficiency for the high speed. But in every case, the LSM technology is the best. So, in conclusion, with reference to the current maglev transportation system, the main advantages of UAQ4 suspension system are passive self-stabilizing and larger gap, high guidance force, no magnetic resistance to motion, and lower energy consumption. Thank you for your attention.
Thank you, Professor Dovidio, for your presentation. We may have time for one question. Yeah.
Sorry,
Wait for the micro.
How does the amount of energy consumed by the maglev system compare to the aerodynamic drag energy?
No, we have in this study we compared only magnetic resistance with rolling resistance. No other resistance was compared. No? Our purpose was to highlight the problem of the magnetic resistance in a current maglev system.
Okay.
So thank you very much again, Professor Dovidio. Then we continue with the schedule, and we have the next speaker is Manuel Kirchner. He's a student at the Technical University of Deggendorf, and he presents the results, I think, of his bachelor thesis, right? And he's entitled about empirical investigation of possible concerns regarding the use of magnetic levitation elevators. Please, Mr. Kirchner.
All right, good morning, ladies and gentlemen. First of all, thank you, Dr. Kirchner, for the introduction. I'm Manuel Kirchner, coming from Germany, currently working for the Flix Mobility in both train and bus sector. And today I'm honored to talk about the findings of my study investigating concerns, possible concerns regarding using maglev elevators. I will guide you through the topic according to this agenda. Firstly, introducing the scientific issue I focused on, and then showing up the empirical approach I used in order to find the results, and the presentation will conclude with a short summary. So why was this topic, why is investigating empirically concerns regarding the usage scientifically relevant? At the time when I did my study, which was in November 2017, the overall public was and still is driven by enthusiasm due to the progress that will be made by this maglev elevator technology. But yet, especially indicated by media coverage, aspects of safety occasionally spark concerns. And the following questions somehow appear to be unresolved but in need of an answer. So I wanted to find out if possible users are actually concerned about the use of maglev elevators, and if so, if the answer might be yes, what kind of concerns, what characteristics exist. The general approach was done via a face-to-face survey to 197 visitors of the elevator test tower in Rottweil, Germany, where the technology is tested at the moment. And it consisted mainly of two major parts. It should be assessed in terms of a subconscious assessment of a possible use. And to these dimensions that you can see, the harmlessness, the safety, familiarity, controllability, and freedom of risk. And an open questioning combined with a concrete assessment of predefined aspects should in total enable to answer the question. Starting with the results, I want to start with the subconscious assessment I already mentioned. On average, people considered a possible usage of maglev elevators to be rather harmless than worrying, to be fairly safe, and a bit between undecided and unfamiliar, while in the dimension controllability, irresolution was dominating. Finally, they considered it to be fairly riskless with a slight tendency towards the middle. Of course, besides these average tendencies, categorical differences needed to be taken into account, which was done by a developed formula, mathematical method in order to assign each and every respondent to these 5 predefined categories of concerns. So we have about 1/4 of people actually being completely free of concerns in using maglev elevators, while about half of share of the people tends to be rather free of concerns, few undecided ones, and about 20% of the total sample seem to have subconsciously expressed existing concerns. Whereas no one really showed strong concerns, at least according to this method that was used. It needs to be noted that the application of the average values I already showed you, so the total sample on average, to the method used for this resulted in the dimension rather free of concerns. Of course, this needed to be validated. So the groups you can see here, the averages inside these groups were backwards visualized in the polarity profile and rearranged. And considering the fact that the harmlessness and the safety, the two upper dimensions, were emphasized more in the formula itself, you can see a clear, and we can see a clear differentiation and a clear differentiation of possible uses in terms of using maglev elevators. And the method itself seemed feasible according to this. As I already told you, there was an open questioning of possible concerns, so people were questioned of naming them if they have such. And about 1/3 of the people actually expressed concerns. Those mainly related to the new characteristics, the novel aspects of the technology, combined with known fears such as power outages. The 5 predefined aspects that were given in order to estimate them according to a potential usage, you can see here. So the average tendency of people, and generally in average, the new novel characteristics for elevator users in general, the technology will bring, were considered to be rather unobjectionable, while especially, as you can see, the fourth one, the levitation of cabins in the horizontal. Yet, again, we can see some categorical differences, while about 1/6 of the sample estimated the magnetic field presence, the absence of ropes, as well as the fact of multiple shafts circulating in the cabins circulating in the shaft, to be worrying, the levitation itself seemed to be the less harmless aspect and the less harmless characteristic. Finally, a few correlations in this not scientifically touched field needed to be analyzed, and a few correlations could be generated. It seems that the harmlessness and the safety, so the assessing the harmlessness and the safety of using maglev elevators correlates with one another, as well as the harmlessness and the freedom of risk. Moreover, the magnetic levitation itself and the absence of ropes, so the two predefined aspects, also correlated with another in the assessment. And in an overarching view, the categorization I showed you, so the individual classification of types of concerns, basically, correlated with the open questioning of concerns, which means if you are a person that can be classified as being rather free of concerns, it is more likely that you don't actually name them, or you don't name them at all when you are questioned openly. This in total brought the study to the following summary. It seems that in the overall trend, and also the main share of people tends to be free of concerns of using maglev elevators, whereas we have seen there are differentiations to be made, and in total 1/6 of the people actually expressed and could name such. Those are mainly of the following nature, as you can see here, so basically health-related concerns due to magnetic field presence, as well as the general uncertainty by mental perception of ropelessness, of absence of ropes. And the magnetic levitation itself caused concerns as well, since people are not that satisfied or don't always believe in the stability of the magnetic fields. Finally, the uncertainty of possible power outages and the feared effects on that, especially on magnetic field stability and carbon maintenance, was one of the most expressed topics. So what does these results mean for further research, for implementing the innovation? Basically, in my opinion, while using elevators has become a daily business for many people, the maglev elevator technology will of course bring some new characteristics and as well framework conditions who haven't changed much in the last decades in this means of transport. And those will definitely, the actual perceptibility of those new framework conditions needs to be seen, of course, but they are definitely mentally both conceivable and perceivable for potential users and for users. So while the main share of people in this respect seems to be completely free of thought, especially these new characteristics for a few lead to assessments and thoughts that differ from tradition and eventuate in actual concerns, which can be addressed when promoting the implementation of these elevators. Thank you.
So, thank you very much, Mr. Kirchner, for this nice presentation about, I think this such an investigation is important for the acceptance of a new technology in this innovative application. So we have time for some questions. Yeah, Mr. Stefan.
I believe that before interview, the 197 candidates, you had to explain what is a magnetically levitated elevator. I would like to ask you, how have you explained to these candidates what is such an elevator? And how much time was necessary for each one? Or I also am curious if you have asked each by each, or if you had an auditorium like this one, you explained what's a magnetically levitated elevator in 10 came the interviews. I hope you have understood my English.
Yeah.
It's fine. Okay, thank you.
Thank you for the question. First of all, I did each and every interview individually, so that was the second part of your question, but I'm going to answer it first. So each and every respondent were asked alone, individually. And the survey itself was introduced by asking people if they actually know the technology. Of course, it was all of them were visitors of the elevator test tower in Rottweil, where the technology is tested. So most of them have at least heard of the technology before, because it's promoted a lot. And for those who were not sure or who said no, I explained them in a media coverage type of style. So I orientated on how media basically describes the technology, because I assumed that those who say yes, I know the technology, also have the same basis of knowledge, maybe hearing from the media. And this was, so I basically pointed out the main characteristics. It is elevators that can drive not only vertically but also horizontally, based on magnetic levitation technology, many cabins in one shaft, and so on and so on. So it's just explaining neutral the characteristics. And for that, it was assured that basically the whole sample had at least kind of similar knowledge for this survey.
So if there's no more question, then I would like to thank Mr. Kirchner again. There's Mr. Wenk.
You talked about the individual categorization of participants. Could you tell us about which mathematic formula you used to classify the participants into groups?
Yes.
Thank you.
Thank you for the question. I can explain, but it's maybe better to show. Maybe we can reopen, if it's possible to reopen the... It's a bit hard to explain a formula without seeing it. Thank you. So, I anticipated this question. And as you can see here, I showed you the polarity profile, so the contrastive pairs that were used. Of course, there were some buffering pairs in between, so not everything was with this somehow negative focus. But I emphasized mostly on the first two aspects, the first two dimensions, since they were the core issue of the whole question, of the whole issue. And by huge theoretical research, I could make up the three other dimensions as being able to express concerns, actually. And with this formula, as you can see here, so each and every respondent basically had one of these, somewhere landed here in each dimension, and the values were just put into this formula. And there were ranges between -7.5 and to 7.5, and it was categorized accordingly. While 0 was only undecided, so only 0 could lead to an undecided estimation. Does that answer your question?
Yes, thank you.
All right, thank you.
So thank you again, Mr. Kirchner, for the presentation. Then we come to the last presentation of this session, and it's from Professor Angelo Jacob from the University of Porto in Portugal, civil engineering and professor at ISEP, Polytechnic School of Engineering. He will talk about prodynamic, a new concept of super elevation in magnetic levitation. So please, Mr. Jacob, the floor is yours.
So, ladies and gentlemen, good morning. I'm presenting you a new concept of super elevation in magnetic levitation called prodynamic, made by myself and my colleague Monteiro from Portugal. Okay, I understand. So the topics very quickly are the very fast introduction, historical reference, magnetic levitation system, and after that I will explain my job. First of all, talking about the super elevation concept and the new proposed system, prodynamic, and last on the conclusions. So we have here an advanced propulsion revolution, as you know, a new concept of land mass transport. It creates height expectations compared to aviation and high-speed railways. It has a best performance in velocity, energy and comfort. It eliminates the friction and the wear between materials. We have major two systems, the transrapid and the superconducting maglev. The article that I bring here proposes an adaptation of these existing systems. In the curve context, it is possible to create rotation magnetism. Capacity of the vehicle to rotate on themselves, thus not requiring the existence of super elevation in the rail. We call prodynamic. So, aviation is clearly the most competitive means of transport for long distance. And for distance until 800 kilometers, the high-speed railways is more competitive. So there is an intermediate range favorable to the magnetic levitation. So, very quickly about story. Over the last 10 years, highly developed rail systems have been created, like the system ICE, TGV, Shinkansen, etc., reaching commercial speeds around 300 kilometers. First high-speed railways appears in Japan, Shinkansen, almost 20 years after it appears in Europe with TGV. In the 80s, the German and Japan began to develop the version of maglev technology. First commercial line is now in Shanghai. So, but we have limitation in railways, such permanent physical contact between two materials, track maintenance with high costs in the ballast railways, rail and well wear. And we have almost a limitation around the 300 kilometers per hour. About the systems we have three systems, I know. The EDS, electrodynamic suspension system, the electromagnetic suspension system, and the Indo-track. There are advantages and disadvantages between the systems. The AMS have smaller magnetic fields comparing to the ADS systems. The ADS system allows high speeds and needs superconducting magnets. So basically we have two systems. On the left we have the Japanese system, on the right we have the German system, as we know. So what about the super elevation concept? I'm talking about the transverse inclination on the track. In order to reduce or eliminate the non-compensated centrifugal force. The centrifugal force is a function of the velocity and the radius of the curve. The current systems are connoted with a rigid and constant physical structures. The situation creates many limitations on the actual railways, such as insufficiency or excesses can't. Super elevation. Pardon me. Physical contact between materials limits the super elevation. In extreme speeds, like stopped or at maximum speed, always create discomfort on passengers. Current systems developed by Transrapid and the superconducting maglev continue to use the rigid structure to super elevating curves. But maybe it is not necessary because now we have no physical contact between materials. How we say in the picture, we have a curve in the Transrapid, for example. With the new magnetic levitation technology, it is possible to control the super elevation. It is possible to have 100% uniform structure without putting super elevation on the rigid guideway. The vehicle also does not require hydraulic suspension to create super elevation. By creating an additional magnetic field, it is possible to create a concept of vehicle rotation along the longitudinal axis. So, how is that possible? Let's see our idea. So, we propose, taking, for example, the Transrapid system, we can modify the guideway structure and the vehicle jaws. We see in the picture, there, we can create in the laterals magnetic field. Also, in the superconducting maglev, we can create a structure to sit the vehicle, like we say in that picture. Constant geometries are defined for the cross-section on the monorail, either in a curve or straight line for both systems. It is necessary to create an auxiliary magnetic field to provide vehicles rotation in curve. Several speeds were tested for a radius of 4,400 meters, evaluating the no-compensated lateral acceleration. Speeds between 30 and 450 kilometers were used, and an inclination, a transversal inclination, had maximum of 12 degrees. An uncompensated comfort acceleration below 1.5 meters per square second. So, this is our concept, a schema of the forces. We have the weight and we have the force centrifugal. So, the results of the calculation we done, we tested on the 30 kilometers per hour until 450 kilometers. And we vary the rotation of the vehicle. So, what do you propose? We propose, maybe it's a challenge, it's an idea, to convert, for example, of the superconducting maglev to on the left side structure, and the Transrapid to the left side on the green row. We study also the geometry to fit that vehicles. So let's take a look about a virtual movie just to show clearly what I'm talking. It elevates and it turns left, to turn right. So we have a guideway constant and we can with another field magnetic to make the rotation on the curves. So another movie, just to see how it circulates. It's a constant rail, constant guideway, monorail. So, in conclusions, magnetic levitation is clearly the next revolution in land transporting. That's clear. We can take advantage on this new technology to change the paradigm of super elevation. With the new system ProDynamic, it's possible to control the vehicles in curves, creating total freedom in the rotation of the vehicle. It's not necessary to change the structure in curves, because the monorail is constant in geometry cross-section. Rotation of the vehicle is only performed in curve, as this rotation has the advantage of adjusting the speed of the vehicle, ensuring the best comfort of passengers. ProDynamic system give a new technology boost when the vehicle describes curves. creating an infrastructure supervision in a monorail and without complex mechanical hydraulic systems. And the main goal of my study was to create a monorail shipper. So in civil construction, we can have a cheaper monorail saving money. It is possible to greatly reduce or even eliminate the lateral non-compensated acceleration. So thank you very much for your attention.
Thank you very much, Professor Jakob, for your presentation about the new concept, ProDynamic. So we have time for a couple of questions. Yeah.
With a mechanical system like in the French TGV that does super elevation, the cost is just in the vehicle, whereas with your system, the cost is throughout the guideway. So that would seem like there's some advantage to a mechanical system.
Thank you for your question. First of all, I would like to say that I'm a civil engineer. I don't know anything about magnetism. So I'm a civil engineer, I'm a projectist of roads and railways, and my objective was to create a monorail. I didn't study the vehicle, okay? I need the help of my colleagues, physicians, electricians, mechanicals, to tell me if is that possible. So I would like to create a monorail cheaper and putting on the floor, not elevated, and it is constant. I don't know if I answer your question, but we can talk after.
More questions? Please.
I want to ask a question. Is it similar to the teetering train you see for rolling stock? Because on curve, we want to increase the crossing speed, we will some teetering, like the Pendolino or X2000 train. So the coach can lead the teetering. We call teetering train. Is it similar mechanism like the rolling stock train, teetering train?
On the train, we have the mechanical hydraulics. So
is it similar?
It is similar, but it's made by another field magnetic.
Okay.
Not with mechanical hydraulics.
Okay. Hydraulic. Normally we
use
hydraulic
systems.
Okay, you use magnetic control. Yeah, it's similar. You see, to increase the speed on the small curve, but within the allowed acceleration range.
Okay.
Is it okay?
Yes, it's okay.
Some more questions? If not, then thank you very much again, Professor Jakob, for the presentation. And just for confirmation, we have no additional change in the schedule. Then this was really the last presentation of this session. And I would like to thank all presenters for their interesting presentations and also for the time management. And also would like to thank you for your attention. And then we can have some coffee. Thank you very much.